What you see here is a decommissioned nuclear power plant. For years, electricity was produced here and of course nuclear waste was also produced. The plan was to find a final storage site for it by 2031. A new report now says that we will probably not find a location for this until 2074. And that means that this nuclear waste will have to be stored above ground here temporarily. But there are also other ideas about what to do with the nuclear waste. These involve electrochemical processing and processing with particle accelerators. This is known as partitioning and transmutation. And today I'm taking a look at the startup Transmutex. They want to build processing plants at the sites of old nuclear power plants, which according to them will allow the waste to decay 40,000 times faster and reduce its volume by 89%. This sounds incredible, and that's why today we are going to take a look at how the whole thing works, what the challenges are, and why the Federal Office for the Safety of Nuclear Waste Disposal considers the whole thing impossible. And with that, welcome to the German Science Guy. I'm Dr. Jakob Poton, and in Germany we say Los geht's. Guido and I are currently in the machine room. This is where the generator is located. It used to generate electricity in the nuclear power plant, but now it is being dismantled. You can see that there are still some parts of it here, and Transmutex now wants to use this room in another way.
Transmutex is a company that has a relatively simple idea, namely to pursue one of Germany's favorite ideas, recycling. We have a lot of highly radioactive waste, including from this nuclear power plant, and it can be separated. Then you get, on the one hand, good radioactivity, so to speak, namely cancer drugs, and on the other hand, you are left with medium-level radioactive waste and about 10% highly radioactive waste. The 10% would then be transmutated, and then it would no longer be radioactive for 1 million years, but only for 800 years, and that's much easier to deal with. And we would put the particle accelerator here in this room.
The idea behind Transmutex is to convert this hazardous waste with a process known as transmutation. This reduces its radioactivity 1,000-fold. The whole process is to take place in a facility called START. START stands for Subcritical Transmuting Accelerated Regenerative Technology. This is a facility in which radioactive waste is bombarded with neutrons. The idea behind it is based on the following principle. When the neutrons hit the long-lived radioactive materials, they split them and transform them into short-lived radioactive or even stable materials. That's the core idea. Now let's take a look at how the whole thing is supposed to work. Whether this whole idea is even feasible was examined in an implementation study by TÜV Nord and scientists from the Technical University of Munich, among others. The study was commissioned by Sprint, the Federal Agency for Breakthrough Innovations in Germany, which is a little bit like the DARPA in the US. It promotes projects that it believes have great potential for solving future problems. I love the Sprint because I really believe in the idea behind it, but at this point I would like to emphasize that I was completely independent in my research and that we spoke with several independent experts, and as always you find all sources in the video description. Okay, let's get back to the idea. The process consists of 3 main steps. First, separating the spent fuel elements from their cladding tubes. Second, processing the fuel, and third, irradiation in the reactor. Within these 3 main steps, there are also a few intermediate steps, which we will take a closer look at in a moment. Before we get to this, let's take a quick look at the differences between the various radioactive substances, as this is relevant here. The starting material is spent fuel elements from nuclear power plants. They contain a variety of radioactive substances that must be distinguished. First, there's uranium with the atomic number 92. This means that a uranium atom has 92 protons in its nucleus. Uranium is a very heavy element and is naturally radioactive. Uranium accounts for about 96% of the weight of spent fuel elements. This uranium consists mainly of uranium-238, the most common natural uranium isotope. In addition, small amounts of uranium-235 are also present, typically less than 0.8%. On the other hand, they contain transuranic elements. They are very long-lived radioactive substances such as plutonium, americium, curium and neptunium. They belong to the chemical group of actinides, all of which are radioactive and belong to the metals. They are the main component to be transmuted. Even though they make up only a very small proportion of the total mass of spent fuel, namely only about 1.5%, they are the substances that emit the most radiation. Okay, Let's get to the Transmutex process. There's an interim storage facility up ahead. That means radioactive waste is stored there in castor containers. And first of all, I have to say, I'm a little surprised at how close we were able to go to it and how low the fence is. But it's a very, very important place because this is where the first big step begins for Transmutex. In the case of nuclear waste, the casing is first separated from the spent fuel rods. Then you have the radioactive material, which is broken down into its components. It's a bit like a high-tech waste separation plant with processing, but with nuclear waste, so it's much, much more complex. But how does it really work?
Yes, we would bring the castor containers from here to the site, from the nuclear power plant, and set up the infrastructure for an electrochemical partitioning plant. There, the material is separated so that 10% of highly radioactive waste remains, which must be transmutated. These are fission products and transuranic elements. On the other hand, you then have 90%. Some of it is radioactive waste, some of it is precious metals, and some of it is radioisotopes that can be used for medical and industrial purposes. These are then filled in and further processed into what we will look at later.
Most fuel elements are stored in castor containers near old nuclear power plants in interim storage facilities. This is one of the reasons why Transmutex wants to build the plant in old nuclear power plants. The fuel elements are to be inspected and weighed in the head-end process, and then their structural parts such as frames and feet are to be removed. The fuel rods themselves are cut into small pieces of about 1 centimeter to expose the actual fuel material. The metal casing are separated from the fuel. Now the individual components of the old fuel are separated from each other using various electrochemical processes. The entire process is called partitioning. At the end of this process, you are left with the following substances. First, small amounts of highly radioactive fission products such as iodine-129 or technetium-99. Second, moderately radioactive substances that can be disposed of in final repository. And third, valuable raw materials and isotopes that can be sold or used for other purposes. Fourth, pure metallic uranium. And fifth, transuranic elements. And that brings us to the second major step: processing the new fuel for the subcritical reactor. To do this, thorium is mixed with the transuranic elements to be disposed of and a little amount of uranium. The materials are then in powder form. They are then converted into a metallic alloy and processed into the finished pellets for the fuel elements of the start reactor. The start reactor is the heart of the system and important for the third major step: irradiation in the reactor.
So now the radioactive waste has been processed, we had the partitioning. What is the next step that is taking place here in the old reactor building?
After partitioning, the 10% transuranic elements are taken, packed into new fuel rods, and then placed in the dome in what I would call a core mill, because I don't like the term reactor.
We call it a reactor because
You can call it a reactor if you are aware that the associations with it are not accurate in this case. Of course, a reaction takes place there, just like in a test tube in a reactor, but it must also be clear that it is a subcritical reactor. There is no independent chain reaction.
Neutrons are required for a reaction to occur. Therefore, START essentially consists of a neutron source that connects a particle accelerator to the reactor via a so-called spallation target. The particle accelerator sends a proton beam to the spallation target located in the reactor. Spallation comes from the word to spall, so something like to splinter. By the way, it's the same in German, that's Spallation, so we also took the English word. And this means when the proton beam hits the spallation material, which in this case is liquid lead, the neutrons are splintered out of the atomic nuclei, and with that they are released. The neutrons then trigger a reaction in which the nucleus of the atoms is altered, so transmutated. So the neutron capture leads either to a stable element or to decay into two smaller elements. Nuclear fission in START is not self-sustaining, so no chain reaction is triggered. Instead, the reaction depends on the supply of neutrons. This is referred to as subcritical, a term that Guido was already mentioning. And this also means when the proton beam that triggers the neutrons is switched off, the nuclear reaction stops within 2 milliseconds.
Okay, and now you want to build the whole thing into the old reactor building, so to speak. There are actually still fuel rods in there that need to be cooled, and I believe they will still be there until 2026. Why this building? Because theoretically there are already places that would be easier to deal with than a place that also contains highly radioactive waste.
It already exists. It exists on a site where there is an interim storage facility. If I want to avoid having to transport the waste, this is a very good building. I have cranes there that can carry materials weighing tons. I have a building that is already protected. That means the reactor is taken out, our nuclear mill goes in, and then I can transmute these transuranic elements there.
So once the radioactive waste has been irradiated with neutrons, then in the end various isotopes remain, which are then vitrified as high-level waste. The radioactive waste is mixed directly without any complex pre-treatment into liquid borosilicate glass, a particularly resistant type of glass. The molten glass in which the radioactive waste is firmly enclosed is poured into strong stainless steel containers. These containers, also known as molds, are then welded to form an airtight seal. The treated waste is then sealed again. After approximately 810 years, the waste is only as radioactive as the original natural uranium ore. This may still be harmful to health, but the range of uranium's alpha radiation is only a few centimeters in air and a few millimeters in body tissue, depending on its density. It can be effectively shielded by clothing and does not pose a risk to healthy skin when exposed to external radiation. In addition to the fission products, there are also residues of the thorium-uranium transuranic mixture, which was a fuel for the START reactor. And here too, the startup has come up with something exciting. These residues can now be reprocessed, mixed again with fresh transuranic elements from the recycling process of the old fuel rods, and then the entire mixture can be used again as fuel for the START reactor. This creates a recycling cycle that can be repeated until there's no more old radioactive waste left. As described by the startup, this process offers a number of potential benefits.
The advantages are that this allows us to reduce radioactivity from several 100,000 years to 800 years. We now know how to store this kind of waste. That means we can build containers that are safe for at least 1,000 years. In other words, we have a completely different safety concept here than what we have been planning in Germany up to now. The second advantage is that we can reduce highly radioactive waste by 90%.
And there are other advantages, such as energy generation. The liquid lead, which is bombarded with neutrons, also serves as a coolant for the plant, absorbing heat from the reactor core. This heat can be transferred to steam generators and with that drive turbines. According to the study, this should generate 600 megawatts of thermal power and a gross electrical output of 252 megawatts. 32 megawatts of this electrical power is needed to supply the plant itself, in particular for the particle accelerator and the recycling plant. The remaining 220 megawatts of electrical power could then be sold. It would be particularly suitable for district heating or for hydrogen or electricity generation. And just for comparison, a wind turbine has about 2 to 5 megawatts on land, so we're talking about several dozen wind turbines in terms of power. Another idea of the startup is to use the accelerator or reactor to produce various radioisotopes that can be used in medicine and also in aerospace. And this has nothing to do with waste, but rather with irradiating elements so that they can be used to make cancer drugs. For example, for prostate cancer and neuroendocrine tumors, so tumors that arise from special cells found in many places in the body, and also the radioactive waste can be used to produce cancer drugs, so certain substances can be extracted during processing. And that brings us to the cost. Transmutex estimates that the total investment cost for the construction of the facility, so the neutron source and recycling and vitrification units, are at around 1.5 billion euros if the facility is built in an old nuclear power plant. This reduces construction costs by around 30%. However, the sale of medical radioisotopes, industrial raw materials and process heat will generate a net present value. So the current value of future revenues is between 1 and 7 billion euros. This is of course a very wide range, 1 or 7 billion, but there are also many factors that play a role here. And that brings us to the big hurdle in today's video. You know it from my videos. Here we take another look at the critical points of innovations, and Guido himself mentions the first point.
These are challenges on the technical side, but I think it's just as important to identify what the political challenges are, especially in Germany. This is difficult terrain, but it's a very emotional topic of discussion. On the other hand, there are regulatory challenges challenges. Genehmigungsrechtliche Herausforderung.
In order to build the complete facility, the Atomic Energy Act would have to be amended because the reprocessing of spent fuel elements is currently prohibited in Germany. A change in the law is of course a very complex and lengthy process, just like the whole project itself. The study assumes that the processing of spent fuel elements will begin in January 1st, 2035. The resulting high-level radioactive waste will be vitrified, and the calculation for the final storage of the waste is January 1st, 2100. Even if the decay time is drastically reduced, the radioactive waste will still have to be processed for decades.
We have a temporary increase in risk for 2 to 3 generations until everything is used up. But after that, we won't have this problem for 10,000 generations. And in that respect, it's a matter of weighing up. Who do I impose this burden on in order to relieve the burden on someone else later on?
In order to accept an increased risk for 2 to 3 generations, the risk of the project must of course be realistically assessed. And before we get to this first point, which is a subject of controversial debate, I would like to say a few words on the subject. There's generally a lot of discussion about the transmutation and final storage of nuclear waste. The team and I spoke to various independent experts while researching for this video to get their assessments of the Transmutex project and final storage. The topic is really complex and almost every expert had a different opinion and agenda, but I would like to give you an overview of the most relevant points in the video. But let's start with the risks of the project.
We know that decay heat was a problem in Fukushima. We have ensured that this cannot happen by using liquid lead as a coolant. As I said, subcriticality and lead as a coolant rule out the possibility of a meltdown or accidents of this kind. And with partitioning, you have to make sure that it happens in patches and vessel sizes that do not exceed certain nominal sizes. But then handling is relatively easy.
The fact is that highly radioactive spent fuel rods must be removed from the shielded containers, dismantled and processed. Here, a risk assessment should distinguish between the different steps. Experts actually classify the reprocessing of all fuel rods as relatively low risk. There's already a great deal of experience in this regard, as there are or were industrial reprocessing plants, for example in La Hague or Sellafield. The fuel production step, on the other hand, is considered to be a greater risk. High radiation protection requirements are necessary here, especially for the people working in production. A complete safety laboratory was built at the ITU in Karlsruhe, it's in Germany, as part of Eurotrans for the production of test fuel. Calculations have shown that it is extremely difficult to keep the radiation exposure for people who produce solid fuel from radioactive waste low enough that it is not harmful to health. That is why, for example, Russia decided against solid fuel. The final step is irradiation in a subcritical reactor. Even though a chain reaction cannot occur there are an incredible numbers of factors that must be thoroughly understood and controlled to prevent accidents. For example, the particle accelerator must operate very consistently. If this is not the case, the accelerator switches off, but this causes large temperature differences in the reactor. Problems in a reactor often relate to reliable heat dissipation. For example, there may be problems with the circulation of the coolant, known as loss of flow, or the heat can no longer be dissipated from the plant, known as loss of heat sink. Switching on and off and the resulting temperature differences can cause material stress, which can also lead to major incidents in the long term. Transmutex is collaborating with the Paul Scherrer Institute on accelerator technology. This is a highly known institute that specializes in accelerator technology, so there is a great deal of expertise involved here. Their goal is to achieve a maximum of 20 seconds of beam interruption per year, but this has not been achieved yet. All processes must be understood down to the smallest detail, and as Transmutex currently describes in its study, some experts do not yet consider this elaboration to be sufficient. Transmutex also states here that it still needs to carry out this detailed elaboration. Well, and information that is considered insufficient is not only criticized in the risk assessment. One of the major critics is BASE, the Federal Office of the Safety of Nuclear Waste Management in Germany. They have written a statement on the study and consider the Transmutex project to be unfeasible as it stands. One of the major points of criticism is that the information provided is insufficient, with no comprehensible information on numerous technical crucial functionalities. I also spoke to Guido about this, who in turn says that in addition to the study, there's also a status report that was not taken into account in the criticism. But he also says that some aspects of the technology are company secrets, and I think it's clear that Transmutex does not want to reveal everything here. Nevertheless, the question is justified. Is a large-scale accelerator-driven subcritical reactor, as proposed by Transmutex, feasible? First of all, there's a scientific consensus that each individual step can be implemented on a small scale. Back in the 1990s, Nobel Prize-winning physicist Carlo Rubbia developed a concept at CERN that was similar to the one proposed by Transmutex. There, he was able to prove that the transmutation process itself works. However, processing on an industrial scale is only done for industrial reactor fuel. There is little experience with the fuel intended by Transmutex, and it must also be processed several times. And also, it is not known whether the entire plant can be successfully scaled up on industrial scale, as it has never been attempted. And then I found something really interesting. There's even an international research facility in Europe that is researching the concept of an accelerator-driven subcritical reactor and attempting to demonstrate the process. The facility is called MYRRHA, and it is being built in Belgium, but Germany, France, Italy and other countries of the European Union have also contributed financially to the project. However, the facility is not yet complete, so no conclusions can be drawn from it at this stage. In fact, research on this project has been ongoing for over 20 years. The commissioning is planned for 2036 and €500 million has been provided by the government. The total cost of the facility is estimated at 1.6 billion. Investors are still being searched for, so it is not certain whether this facility will ever be completed. We spoke to a researcher who was involved in the project himself, and he said that usually not enough money is raised when the investors are not convinced. Of course, we don't know exactly why they shouldn't be convinced, but overall the construction is simply very complicated and takes a long time, so it's a high-risk investment. And you can see why some people don't want to do this. And this naturally raises a question of whether Transmutex will be able to complete the construction of such a facility by 2035. Well, there are some differences. MYRRHA is physically larger and uses a linear particular accelerator, but Transmutex wants to generate significantly more power, namely 600 megawatts instead of MYRRHA's 100 megawatt. Another point of criticism is that the splitting process releases plutonium, which could theoretically be used for weapons. Transmutex considers this scenario to be very unlikely.
Firstly, we have seen that we transported 50 meters from the Interim storage facility to the partitioning plant, which is secured against terrorism. There it is split, processed and returned. So we were inside the nuclear power plant earlier. Just getting in and out of there is quite an achievement. So the idea that someone could go in there and siphon off something is pretty absurd. Of course, I'll split it up. But here too, we have developed a process that ensures we will not expose weapons-grade plutonium in such a way that it could be used.
Okay, and a few other points have also come up, namely that a large part of the financing is for the production of radioisotopes. Of course, there are other ways to produce these radioisotopes, and this complex structure is not absolutely necessary. And in Garchingen, at the Technical University of Munich in Germany, this is even supposed to happen really soon. In addition, one might naturally ask why other countries that still operate nuclear power plants, I mean, we in Germany, we don't do this anymore, do not have such transmutation facilities. For example, France or Japan. They have reprocessing facilities, but no transmutation. And the cost estimates have also been questioned by some experts. Currently, a nuclear reactor in Europe costs already around 10 billion euros. Transmutex estimates 1.5 billion if the plant is built in an old nuclear power plant. However, the Transmutex reactor also generates less energy and is smaller, yet the differences here seem very high at first glance. But Transmutex wants to recoup the money through medicine, energy and raw materials. Okay, perhaps you now understand what I meant by the controversial debate, but let's come to a conclusion. Reducing the radioactivity of waste to 800 years and reducing the volume of highly radioactive waste by 89% are tempting prospects that Transmutex and Partitioning and Transmutation hope to achieve. Although the individual steps work on a small scale and the individual elements, such as high-performance accelerators, have been in operation for decades, scaling the entire system to industrial scale has not yet been attempted and poses technical challenges. And it is also quite clear that working with highly radioactive material always involves a certain safety risk. The same applies, of course, to storing the waste above ground for a long time. I'm undecided in the end. On the one hand, the promises sounds really good, of course, and it has to be said that the waste is there and we can see how complicated final storage is, so yeah, a solution would be really interesting, a solution that helps us at least to reduce the risk. On the other hand, there's still some technical challenges and I'm very curious to see how they will be implemented. And also the financing part is a problem to me, because we all know it's easy to produce waste, nobody wants to take care of the waste. But what do you think about it? And also I would be very curious to hear how nuclear power is discussed in your country, because in Germany there are many people against it. But maybe it's different in your country because there are a lot of countries that still use nuclear power. And also I want to know, what do you think? Should we pursue the Transmutex approach, or do you think that, for example, geological disposal over 1 million years is a better choice? I'm really curious to hear your views in the comments, and at this point I would like to thank Transmutex and Sprint again for the insight, and of course all the experts who took the time to talk to us behind the scenes, and also thank you very much for watching, it means the world to me. And I say Auf Wiedersehen, which means goodbye in German. See you next time. Bye, your Jacob.